welcome to this deep dive. For you listening today, our mission is to crack open this 77-page developer guide from StoryBuddy's Playwright.
Yeah, specifically on the NVIDIA Nemotron 3.5 Lightning model.
Exactly. We are going to unpack exactly how developers are, using this model to build ultra-fast, local autonomous AI agents.
And this guide drops at a pretty critical time, because we're currently in the middle of what Chapter 1 calls the execution layer crisis in agentic AI.
Right, the execution layer crisis, which I like to think of this crisis like hiring a brilliant intern who knows basically everything about everything.
Right, a total genius intern.
Yeah, you hand them a massive project and they deliver incredible insights. But and this is the kicker, they take 3 weeks to answer a basic email and their salary single-handedly bankrupts your whole department.
That is exactly where we are with highly capable AI agents right now. They're just simply too slow and, well, way too expensive for constant everyday deployment.
Oh, for sure.
So to fix this, you can't just throw more raw computing power at the problem. You really need a fundamentally different architecture altogether.
Which brings us to the core trick, right? The core mechanism of Nemotron 3.5 Lightning. I noticed in the guide they're using a mixture of experts, or MOE framework.
Yeah, MOE is huge here.
It sounds complicated, but looking at the specs, it's essentially this massive resource management trick. The model houses 30 billion total parameters, but it only runs at 3 billion active compute speeds.
Wait, so it has 30 billion brain cells, but only activates 3 billion at a time.
Exactly. That routing is the absolute secret to the speed. It's a huge shift from standard models that basically force every single parameter to process every single prompt you give it.
Okay, so is it like having an entire university faculty on standby, but instead of waking up the whole campus to solve a basic math problem, you just ping one specific professor in the math department?
Yes, that is a perfect analogy. And taking that university idea further, you aren't paying the energy costs or waiting on the latency for the whole faculty either. Right, that makes total sense.
You only pay for the specific expertise you need in that exact millisecond. So that routing gives you 30 billion parameter intelligence at 3 billion parameter speeds.
Wow.
But, MOE is really only half the equation for the 4 times throughput increase they are seeing.
Oh, right. Because they also pair it with speculative decoding and multi-token prediction, which means instead of the traditional method where an AI generates one word, checks it, and then generates the next, this model is predicting whole chunks of text ahead of time.
Yeah, think of it like autocorrect on steroids.
Autocorrect on steroids, I love that.
Right, so the model is drafting entire sentences ahead of itself in the background. If its future guesses are correct, it accepts them all instantly, entirely skipping the traditional processing time.
That's wild.
And that is how we get latency down enough to make agents truly interactive.
Okay, so the speed and cost bottlenecks are handled. But, if we're talking about always-on autonomous workflows, these agents also need massive memory to track what they're even doing. And the guide highlights a 1 million token context window.
Which is staggering, frankly, for a locally deployable model.
Right.
And deployment is highly accessible, too. You can run this on everyday local hardware using frameworks like Ollama, llama.cpp, or Unsloth.
Okay, so those just compress it.
Basically, yeah. They compress and optimize the model so it doesn't melt your laptop's hardware.
Good to know.
And then, if you need to scale up to enterprise production, it integrates with engines like vLLM and TensorRT LLM, which are specifically designed to maximize server hardware efficiency.
Having that much context memory is great, but here is where I kind of have to push back on the autonomous side of things.
Okay, go for it.
If this hyper-fast intern is operating independently, like using integrations like Hermes Agent or KiloCode to actually write scripts or query live databases, how do you prevent it from accidentally deleting the company server?
Well, yeah, that is the exact risk of high reliability tool calling.
It's scary stuff.
It is. And it's why the guide really emphasizes that the deployment stack matters just as much as the model itself. To prevent those catastrophic errors, developers are using a tool called Nemotron for security sandboxing.
Okay, Nemotron. So instead of letting the agent just roam free on the system, Nemotron isolates it. It's like giving a contractor the keys to one specific room to fix a pipe, but physically locking them out of the rest of the house.
Precisely. The agent can execute its required functions within that isolated environment, but it physically cannot access or break systems outside of its designated sandbox.
Wow. Okay. So what does this all mean for you listening at home? The big takeaway here is that this guide isn't just announcing a new model. I mean, it's a blueprint.
It really is.
We now have the architecture to build self-healing, always-on AI agent fleets directly on local hardware.
We are crossing a threshold here. We are moving from AI as like a reactive answering machine to AI as a relentless, highly secure, efficient workforce.
Which leaves me with one final thought for you to mull over. If we are now deploying these self-healing AI fleets that can execute complex tools autonomously and securely, I mean, how long until this lightning-fast intern starts rewriting and optimizing its own tool stacks while we sleep?